So we're back. We're going to see the last two scripts, which also take much more amount of time. We've seen the state manager, we've seen the variables of the state manager, we haven't seen all the logic inside it, and we also need to see how we actually move our character. So let's go handle movement player. This is what handles everything that has to do with moving our player. It's going to start with the state manager. Of course, we need reference to the state manager and our rigid body. Do angle check, leave this to true, is what makes the character stop when you're running and changing, very fast changing directions. If you run, let's fall like that. Okay, I'm running and I'm slowly turning, then my character doesn't stop. If I very fast change direction, then he's going to stop. That goes for camera movement and actual movement direction based on the input. And what you can do over here with the guy turning around is, if you have even more animations, you can actually tailor this and make it so that it looks even better, But because we do not have a lot of animations into our disposals, then we're going to use what we have. So degrees around threshold is the threshold between the degrees between them, our moving direction and where we actually are. Use dot is if you instead of using degrees, you want to use the dot, so you actually have a lot more threshold, and it's going to compare with the dot product of the two vectors instead of the degrees between them. Okay, you can use this. This one can be more precise, this one can be more gameplay friendly. And this one, if we turn this to false, you will see why I do not want this. It's going to ignore all that behavior. Okay, so if I'm running and turning around like this, you can see our character sliding around, which it's not really what we are here to do. But just in case you want to to close that, then it's this boolean you need to turn to false. Okay, play with these two, see what you actually feel that it works best, and as I said, I'm going to use the use dot over here. Override force in angle and playing stopping animation, and I think this one is not needed. Yes, I was correct. Okay, in angle, rotate timer, velocity change, and apply jump force. We will see where all this comes into play. Store direction, input handler is the reference to our input handler. The current velocity, target velocity, previous angle, previous direction. Override direction, override speed, force override timer, force over life, stop velocity. And now I realize that me saying the variables names doesn't actually explain you anything. But anyway, let's move on, let's ignore that and move on. So when we initialize this, so when this is the start, this gets initialized inside the input handler. So from the input handler, we also need to pass the state manager. And here's a dumb thing I did. Okay, we initialize the state manager, but I have here get component input handler. So instead of doing that, I could have just do input handler. Let's call this I, or in H, or something like that, and use this, apply this over here, and inside the input handler add a comma and write this. Okay, so you do not have to use get component. We assign the input handler, we assign the states, we assign the rigid body from the rigid body we have taken from the state manager. So that means the state manager needs to initialize first. Okay, execution order is important. And we also go on the animator and close the root motion because it's going to interfere with everything else we have. As I said, if you have root motion, that means you have a lot more animations in your disposal than what I have. So tick is the update, which in truth is the fixed update. Okay. If you are not overriding force, which means you are moving regularly, override logic. We'll see this in a bit. We need to handle the drag depending on if we are moving or not. To handle that drag, then oops. Okay, if there is movement on horizontal or vertical, or if we are on the air, then the drag will be 0. Else the drag will be 4. So you're not also sliding. But since we are placing the position like this, yeah, the drag will come. Yeah, the drag also works when you're on the air too, and that's why we set it to 0. So yeah, it's useful. Otherwise, your character might slide away, even if you're not moving. So, yeah, hand lag. If we are on locomotion, then we play movement normal. The logic for movement normal is this. We check to see from the stage angle if we are actually inside the in-angle move direction. And over here, we need to get again the two vectors that has to do with vertical, and horizontal. And why I didn't set that inside inside the update state info, even though it's exactly the same, is, I don't know. Yeah, there's no way why. Yeah, you know, it's one of those days that you just write and you do not know what you're writing. But anyway, let's keep this way. It's exactly the same as we have inside the input handler, as you can see. And yeah, I think I know why I did this, because if I had to change any of this, I didn't want to change any of this, so I'd rather just do it again instead of doing it over, you know, instead of changing values that I use on another script. Okay, it's not really any performance heavy, this is just a multiplication. So yeah, let's go with this. Okay, similarly again as we did on the input handler, we reset the 0, and if we are on the ground and if we are on locomotion, then we're going to call the function that rotates our character based on the vertical and horizontal vectors we have over here. The target speed will start as walk speed, and if we are running and the ground angle is not, and the ground angle is 0, then that means we're going to set our target speed to be the running speed. So whenever we are going into an incline or a decline, then that means we're going to override our speed and we're going to use our walking speed. If we are in angle, then we're going to apply velocity to our character. Otherwise, we're going to override the actual velocity of the rigid body to be vector 3.0. Okay, simple. Handle animations normal is what handles the animations. Let's see this in depth. Handle rotation normal. And let's see them and watch them in order, actually, so we do not forget something. Handle velocity normal. You need to pass the two vectors and float speed. We find our current velocity with our own rigid body velocity, and if there is movement, and we check if there is movement by checking if there is actual this state horizontal is not 0 and vertical not 0. Of course we can make this into a single boolean, but that will just take the fun out of refactoring, right? And then we find a target velocity, and that will be those two vectors combined, also normalized, multiplied by the speed we are moving. And velocity change is 3 is the speed we are going to change the velocity, and if there is no movement, we're going to set the target velocity to be 0, and we're also going to go slower. So we start, so there is the acceleration is faster and deceleration is a little bit slower, just for, you know, so just for to have a little bit more naturalism. And then we're going to create the velocity, which is actually lerping from our current velocity towards the target velocity we find over here, based on time.delta time multiplied by the velocity change, and we assign that to our own rigid body velocity. So we override forces into our rigid body. We're not using add force, we're overriding the forces. If there is an obstacle forward, then we're going to reset the rigid body velocity to be vector 3.0. Okay, fairly simple. We find the direction we want to move, we lerp our current velocity towards the target velocity. The target velocity is basically our moving direction, and yeah, we apply that into the rigid body. Handle rotation normal. I have this normal because on the third person shooter we're going to name this to aim. Handle rotation normal, and we need to check if there is movement, and basically it's the same like this, by written like this. Why these are changed, are different, and yeah, maybe I was drunk when I was writing this. Anyway, as I said, that will take the fun out of refactoring, so let's keep it. Okay, store direction. Again, we find we need to store this time the direction we have on our vector horizontal normalized, and then we need to find the target angle. And to find that target angle, we use mathf attenuation 2, store direction x and store direction z. So this will get you the angle between the z and the x, and we multiply that to turn it into degrees. So if you are running and you have enabled the angle check, then you can use either of these two ways to play the stop animation. Those two ways are if you are not using the dot, or if you want to use the dot product. If you are not want to use the dot product, then we're going to get our previous angle minus the target angle, and if that returns us it's higher than our degrees run threshold, so it's higher than 8, we have set this, okay, to be 8, then it's going to reassign again the previous angle to be whatever the target angle is, and it's going to call the function that goes and plays. Okay, this is a little bit further below. It gets from the statics the integer, the ID of the animation special you have over here, which in this case is run to stop. It updates the special to be true, even though you actually do not need the special to be true to play the run to stop. So what will have been wise is we have this set as bool sp true. Let's set it to true because I may have used this anywhere else. So we're going to set this up over here. Okay, we can pass now. If we do not pass something, then this will pass as true. Have it over here, special. It sets the integer like this, and it also starts a coroutine that closes the special animation, and we will see this in a bit. Let's try with false. Okay, and it's going to return back. It's going to go outside of the handle rotation because you are playing a stopping animation. Otherwise, if you do not return, it's going to play. It's going to rotate while playing this animation. That is a problem, of course. If you are using the dot product, then it's going to find, instead of the angle, it's going to find the dot product of these two vectors, of your previous dir and your moving direction. If the dot is lower than 0, so that means it's further than 180 degrees, or yeah, I think maybe it's further than 90, but it's minus 90 and 90. I have to check on that. Anyway, then it's going to assign the previous direction to be whatever we have on our moving direction. If you do not assign it, then it's going to be using it's going to also be using the previous direction again and again, so that will be a problem. Okay, and then it's going to again play the anim space around to stop, and it's going to return. Now have all this. After that, we again assign the previous direction. We need to assign the previous direction because in case we do not return, and we also assign the previous angle even if we are not using it, and we store the direction on the direction we store our own transform.position. We need to find a target direction, so that will be store direction minus our own transfer position, normalize. So we have a direction we want to rotate. We reset the y, we set it to 0 basically, and if that target direction is equals 0, so we set the target direction to be our own transform forward. We are already looking towards that, so we need to set it as a transform forward. We create a target rotation by using quaternion.look rotation, and we have set our own transform by using quaternion.spherical erg transform rotation, target rotation, velocity change multiplied by time.delta time. Okay, simple, very simple. Handle animations normal, place the animations basically. We have our moving direction, so we need to change that into relative direction, so we use inverse transform direction with our state's moving direction, and we get a relative direction. So to move forward, then it's going to get the relative direction z. If there is values on the relative direction z, that means we're actually working. Otherwise, to rotate, it's going to use any values we have on relative direction x. If there is obstacle forward, then it's going to reset the vertical to be 0. Okay, then it's going to apply it to the vertical and the horizontal based on point to dump time and time.delta time. Handle jump, and here's how we jump. A lot of you have asked how we jump. Well, this is how you jump. If we are on the ground and on the stage we have enabled to jump, and we can actually jump. If the stage says there is jump input and we're not currently jumping and we are on locomotion and the current state is not character state hold, and the state's current state is not, we are not on the air. Okay, what's simpler than that? So let's be serious. Jump input, the player has pressed to jump basically, and he's not already jumping, and he is on a state that he can actually jump, and we are not saying hold because you have already pressed to jump, and we are not on the air. Although this with on ground is kind of redundant, but it's also useful because we change the character states. But so let's keep it. That's what I mean. If we are on the idle state, so we are not moving, we're going to set this to be we're going to set the special to true, and we're going to set the integer to play the animation jump idle. Okay. If we are moving, and we see if we are moving from character states, and this is the case with the above actually. With this, you can change that to the state, to the state from the state manager to use this one, this if statement, and probably won't have any errors. I have to test that. I do not know if that will work for sure because I do not remember where we update, how we update this. We have to check this. Here's where we actually jump. So to prepare for a jump, we first need to see the leg front is what mirrors the animations based on which leg is forward at the moment of the jump. Okay, let's see this in a bit. Then we say on a stage jumping, so the next frame that comes through this is going to ignore all the stages. So we only initialize for a jump once. We again set the special type to be true, and this time the special type will be run jump. Then we set the current state we are actually in to be hold, because if we are not on hold, then on the next frame we are going to be on air. The on air state actually looks towards the ground to see if we are on the ground. So you're basically, if you're trying to jump, you need a few frames that you're not checking from ground, because you actually want to go up. And because the on ground function actually places us and hardcodes our position on the Y to be placed on, where that raycast hit, we need a few frames that doesn't happen. So we're going to set our current state to be character states hold. We set on air again with this, and I have already set it. So I guess I was just lazy over here. Okay, statics on air, true, states can jump equals false. So that was the first frame we want to jump. So we do this, and on the next frame we have initialized. We have initialized our jump. So on the next frame we're going to come over here and see that the states are actually jumping. So if we are actually jumping, we have not jumped yet, and we're still on the ground, and we haven't yet applied the jump force, we're going to add a coroutine, add jump force. It also takes, if you want to add a little bit of delay, you can, just in case the animation, needs a little bit of delay to look correct. But with the animations we have at hand, this works just fine. So okay, we apply jump force. And if we are on the ground, stage zone jumping will be, if we are not on the ground, then stage jumping will be false, and else there's no else. Okay, so this will start the coroutine, and this coroutine is going to go and apply us the jump force. So it's going to wait for the delay we have over here. It's going to set the rigid body drag to be 0. We need the velocity we're currently in, and we also need our forward. And the force we're going to apply is, we're going to get our forward, multiply this by 3. We assign the Y to be whatever we have on our jump force, and then we also assign the rigid body velocity. We assign the velocity. So the forward will be a little bit, it will be the force we add, also forward. If we're only adding on the up vector, that can be a little bit of a problem. Well, not a problem, it's only going to jump upwards, and no matter the force you have when you're moving. Okay, so it will just do a small jump upwards. By changing this, it's going to add more force also forward, so you can have a complete arc when you're jumping. Okay, and we have this, we assign it as a velocity, but we need to also close the jump, and to close the jump we start a new coroutine that waits for 0.3 seconds, which basically just enough time that our character has cleared his legs off the ground. Okay, and we have also apply rigid body forces. We're basically on the air. So we change again our current state to be current state on the air. We set jumping to false, apply jump force to false, can't jump to false, and we also say start another coroutine, enable jump, which what this does just re-enables the states can jump after 1.3 seconds. And we do this because there was a problem with this. Yeah, there was a problem that you could actually double jump with this, so that's why I just passed another second over here, just so that we are sure that you have cleared off the ground, so there's no double jumping. Handle drag, we've seen this. Okay, handles the drag. Play animation special, we also seen this. Close special on animation, we use this. Start coroutine. It just waits a bit of delay. It has a little bit of delay and closes the special boolean just in case we haven't had it and we have forgot it to close it based on another state. So for instance, if I have forgotten this to add this script, then this will take care of it. Otherwise, you know, your character was going to lerp, was going to transition back from state to state. And these two functions are used to override the forces we add on our character, and we've seen on the first part of this where these are useful. So we call this function the direction we want to pass for, the life of the force, the actual force, and if on the end we want to clamp. So force over life, override speed will be the force. Okay, override force will turn this to true. Force override timer, we reset the timer. Override direction will be the direction we are passing. We reset the rigid body velocity because we are going to add forces on top of it. We not want even more forces on top of it. Okay, so this kind of makes it a little bit easier to handle the forces that we jump, or a little bit more predictable if you want. Okay, stop velocity, we're going to whatever we pass from the clamp. Override logic is what actually adds that override force. We reset the drag to 0 since we are adding forces. We're going to assign the rigid body velocity to be the override direction multiplied by the override speed, and we keep adding to the timer. If the force override timer is higher than the force over life and we have tick stop velocity, then we're going to also set our rigid body velocity to be vector3.0. We stop the velocity and we override force, so we stop overriding we stop overriding our forces. And override logic goes back again into the update, or the fixed update. So actually the fixed update, as I said, and this will be whenever we are overriding the forces, we're going to reset horizontal and vertical values, because after you have lived the override logic, there might be some values over here, so it will make your character blend, you know, from rolling around to walking completely. So you do not want that. You want it to have a more, you know, if you can trace the steps of the animation, I think it's just better. It just looks more natural instead of just lerping into a walking state animation. Okay, of course you can experiment with this, and depending on the animation you can get something look even more decent. Okay, and we use this if we have taken this one. So back again, add velocity. If you remember from the first video, we use this inside the add velocity animator state behavior. When we're going to add in another video or another tutorial entirely, or another series, a death animation, we can use a similar function to this, and also add some velocity when you're dying, if you do not want to use ragdolls, for example. Okay, so that was it, how you move your character. Let's see the bulk of the logic, which is inside the state manager. We've seen all the functions, and we also seen the initialization phase. Let's see where everything else is. Tick. Okay, the fixed update of the state manager. Otherwise, obstacle forward and ground forward will always start as false. If we are on the ground, we have a function that controls if we are on the ground. And we come over here, we start as false, and if the current state is character states hold, then it says return false. Okay, you're not on the ground, I do not know where you are, we do not care where you are. Okay, hold is, as I said, is for special cases. Okay, we are not on character states hold, then we can do the rest. We start with our origin, our own transfer position, plus a little bit, not a little bit, about the height of the collider. It doesn't have to be precise, the exact position of the collider. And if you do not remember, the collider is okay. This is 0.5, this is 0.55. I just have it this way, so you know, to pass my point across that you do not have to have it at the exact same collider. The exact same position. We start with a new raycast, and we do this because we also have a boolean if we have hit ground or something, and we pass this into another function that actually looks for the ground, and here's where we're going to use ref hit. What ref does is that if you pass a variable, so for instance is hit, it starts as false. Excuse me for that. So where I was, so we have is hit starts as false. Okay, and we're going to pass this if hit inside the method. This method will be find ground. Now, if a variable that is also a ref variable changes inside this method, it's going to change the above variable too. So it's going to also change the variable over here. So if inside this method is hit turns into false, it's also going to be assigned, whatever is hit is assigned inside the method is going to be assigned over here. Same with the hit. Okay, so we're using ref hit. Let's see the actual find ground. Find ground is this. You can see how we set the signature basically for the method. Ref reka is hit, ref bool is hit, and we use it this way. So this is this you can assign it this way too. But this is not actually that much important, since there is actually, let's delete this and we will see if this is going to work. Oh yeah, it's not going to work because there is this hit too. So probably this doesn't need to be like this, or does it? Let's see. Yeah, it doesn't. So I was probably trying to do something else over there and got carried away. Okay, so the raycast hit doesn't need to be assigned as ref, since we are already doing this over here. Although over here we did not do that, so I guess it was already correct. Anyway, keep it this way and we will see. Since it works, who cares? Okay, find ground. What this does debug draw array. Okay, just so that we can debug it, and we have it does a raycast from the origin down, and it assigns it on the hit, ground distance, and the ignore layers which we set in the initialization phase. And this was not over here. This was Okay, inside the init, ignore layers, the ignore raycast layer, which is Unity's default, and the 8 is the layer that the game object is, and you also need to go, we assign it over here, and you also need to create that layer. Okay, you need to go layers, add layer, and add a new layer, and name it anything you want. And yeah, we've seen the rest on the previous part. Yeah, we've seen it. Now let's go where we were, over here, find ground, ignore layer. If we hit something, then it's going to turn is hit to true, and since this is a ref boolean, it's going to also update the hit, the boolean above, outside of the method, and this is going to either return the hit, if so we need the hit, and it's also going to assign the hit, since this is also a ref variable. It's going to assign the hit even if you do not use it as a return hit. And you can see that I use this over here. Okay, similarly I've actually can do this, and it will be exactly the same as having it as this. Okay, and yeah, let's try it this way actually. Let's see if it works, because I'm curious. It's probably going to work though. Usually, you know, when I test stuff, yeah, I might forget to fix stuff otherwise. So, did you notice that? No, you didn't, because there was no error. It actually worked exactly the same. Okay, enough with that. Let's go back. Let's delete also this. This finds our ground by doing a raycast. Now let's go back and above. Find ground. Now, if it doesn't have a find anything, we need to take care into account that, you know, this collider and the way it is, since it's a capsule collider, or it can be a sphere. Okay, the raycast goes directly. Let's hit play again. The raycast starts directly in the center, but if I'm jumping, you can see we need to take care into account that we actually clear our own collider. Of course, you can use a capsule collider, or not capsule collider, a sphere cast or a box cast or whatever, or you can do it this way. It's exactly the same. And yeah, okay, so without that, if it was like this, without doing the extra raycast, the sender would have said that it's on the air, but we will be stuck over here. Okay, because that's the way the colliders work. So we're going to do a for loop. We're going to find an origin, which our origin is going to be taken whatever we had from over here, and we have a switch depending on the value of the for loop. So the first one will be forward, so it will be plus forward subdivided by 3, backwards, right, left, and then right. Okay, so if in any of these for loops one of these turns true, and how it can turn true, it's going to be updated from doing the find ground again with a hit and is hit. Okay, then it's going to get is hit. If it's true, then it's going to skip all the others. So if the first one finds something, it's going to keep making the rest. If none of these find something, then that means we are on the R. Okay, yeah, that's it. The on ground return value will be assigned whatever you have on or hit, and if the value is false at this point before we return it, then we're going to get our target position, then yeah, I'm stuck because, you know, I've recorded 3 videos today. And yeah, if the return value is not false, so it's true, the target position, we're going to get our own transfer position, and we're going to get our target position .y, hit point .y. We're going to add any ground offset we have, and then we're going to apply it into our own transfer position. Okay, so we have target position. Okay, so this little bit part of the code is what keeps your character afloat. Okay, because the capsule collider does not touch the ground, we need this raycast that is exactly at the position that if this capsule collider was touching the ground, and we are placing our character like this. So think of it like you know, offsetting the collider. But if there was any collision like this, any small collisions especially, it was going to ignore this. And the reason why I did this was to take care into angles like this one. Okay, so this will keep the character sticking on the ground like this. But the bigger problem will have been with the other colliders we have made in the past was that we're walking on an angle towards and going upwards of an angle, then we will have problems because the collider will have hit this the collider of this incline, and that will have been a problem, as you can guess, because the collider will need other forces, and the forces you will have to add will have to take into account the incline, and so on and so on. And yeah, faster way, cheaper way, and the easiest way, I believe, to do that, to ignore any problems that might arise from an incline. Okay, or the easiest way I could find. Of course, we are free to do as those, I think, Murphy's laws are. Somebody is bound to, after you have spent 5 hours thinking of something, somebody is going to create something better afterwards in a less amount of time. That's how technology works. So yeah, this finds if we are on the ground and also places us on the ground. If it's on the fine ground, let's go back. We are over here. Okay, this controls if we are on the ground and also places us on the ground. If we are on the ground, we again find a new origin, and we need to see if we have any obstacles forward. Okay, to see if we have any obstacles forward, we're going to get on from our origin, and we're going to add vector 3 up, so we're adding 0.75 on our origin, so that means is about, let's go into a normal angle, so that is about this line. Okay, we're talking about this line. Yeah, so that does a raycast forward, distance check forward, the distance we're going to check, and again we pass the reference of obstacle forward into a new function that actually does the raycast. So let's go into this function, and this is kind of 2 parts. It has these 2 stuff, but for now just keep in mind that the only thing that we need for right now is the raycast, which does a raycast from origin to direction. And yeah, if it finds something, it's going to either set is hit true and false, and it's also going to get to take the is hit as a reference boolean. So if the is hit is updated, then it's going to update it also on the variable we're passing. Back again is clear. Okay, origin, transfer forward, distance check forward, and if it finds an obstacle forward, then it's going to also update the above variable. if we haven't found an obstacle forward, that means we can check, we can walk forward, but we need to know if there is ground forward. And if there is ground forward, we also need to know what angle that ground forward is. Okay, simple. What can be simpler than that? So the new position we need to find if there is angle forward will be on the origin. We have already added the 0.75. We're going to add transfer forward and plus 0.6. Okay, so it's not exactly at 1 point forward, it's a little bit less, because yeah, this will work just fine. You can add more, but there's also no need to add more, to be honest. And we're going to use again the is clear origin minus vector 3a, ground distance multiplied by 3, because the angle might be, you know, it might be an acute angle. Now, if you do not know what an acute angle is, okay, this is a right angle, this is 90 degrees, this is if it's higher than 90 degrees is an obtuse, as your math teacher said, is an obtuse angle. If it's lower than 90 degrees is an acute angle. Okay, and we need to have ground distance higher than basically we need to see if there's ground forward higher than the distance we normally check if there is ground, because if we have an elevation that is like this, that is an obtuse angle. Okay, if we are looking, if we are sitting over here and we do a raycast down and we find ground. Okay, if we are looking at the same position again to find ground, then that means we are hitting on the air, because this is a steep angle. So we multiply this and we get it to look further down until there is an angle like, yeah, even if there is an angle like this, we can walk downwards to an angle like this. So basically this controls into what angle we can walk. So that's enough for that and my amazing painting skills. I know, do not be jealous. It's all about learning. So yeah, if there is an obstacle forward, then we have to check what kind of an angle there is with the obstacle. So we're going to see if there is an obstacle forward and we actually want to walk towards forward. So we're going to check the angle between our own transfer forward and our moving direction. So if we hit a wall, so if we are here, okay, our forward is this, so it finds a wall over here, so it has an obstacle over here, but we also need to be able to move all these other directions. So if our moving direction is like this, so it's greater than 30 degrees of an angle from our own transfer forward, then that means we can actually move forward, we can move freely, just not towards that obstacle. Okay, makes sense? So if the angle is greater than 30, then we're going to reset the obstacle forward to be false. And basically that's how we can check if we are on the ground or if we are if we have obstacle forward, and the angle between the, if we are going to go into an incline or a decline. And we will see in a bit the other stuff that is inside is clear, because it has to do mostly with animation. Update state and monitor air time. Update state is after we have passed everything on the state manager and we've done all these checks, and it's going to go into update state and it's going to check if the current state is hold. Do not do anything over here. If it's not hold, horizontal will not be 0, vertical if it's not 0 then we're moving, If it is, then we are on idle. If we are not on the ground, then we are not in any of this, we are on the air. Okay, so basically this updates the enum. Fixed tick only has this. It's, again, we use this inside the update. You can use this also inside late update, and we update this from fixed tick. If I do not have this, if I remove the second check we're doing, you're going to see that when I rotate, you see the feet of the character, sometimes it goes through the ground. Okay, and not always, but at some point I actually have made him in the past to go, and you can see on some other cases that he goes. I've actually have made him go almost halfway in the ground. Okay, you can notice it only a little bit. So with this, you can never notice it because it actually, after everything has run, it goes and fixes this again. It fixes his position. And again, this is just the regular update. This is the fixed tick. This is just the regular update. Let's call this regular tick. Let's call this fixed tick, just to make sure we do not get any problems. Regular tick, fixed tick, fixed state manager, regular tick. And that's the update state. The on ground function, find ground, we've seen this, ground, monitor airtime, and leg front. Monitor airtime is if we're not jumping, and if we're not jumping, we're going to set on the animator, the boolean on air, we're going to set it the exact opposite of our on ground. So that means if we are on the ground, then we're not on the air. If we are on the air, then we're not on the ground. Okay, very simple. If we are on the ground and a previous ground variable where we stored where we were on the previous frame is not the same as the on ground, then that means we are coming from the air towards the ground. So this controls which animation is going to play, okay, which landing animation is going to play between these three. How we control this? We're first going to check, are we over the airtime, is it over the airtime threshold, so we know it's a long jump, and depending on if we are pressing any buttons, 2 is roll, 1 is the hard landing. What you can do also is, you know, add more checks with airtime threshold. Instead of doing a check with if there is input or not, you can make him roll, or do the opposite. If hard landing, if it's higher than 3 seconds on the air, then that means it's a longer fall, and stuff like that. Okay, I'm going to leave all this entirely up to you to see what you want to do with this. And then we can also going to reset the airtime. Now if we're not on the ground, then we simply add airtime. And finally we're going to update previous ground with whatever on ground we have. Leg front is, as we said, is whenever we are jumping, finds which leg is on the front and updates the mirror jump, which basically mirrors all our animations that have to do with jumping. Now, how we see this, how we compare how we can find which foot is forward than the other. Left leg or left foot, I guess, more appropriate. We use, of course this will only work for humanoid characters, we use anim get bone transform, human body bones, left foot and right foot. Okay, and we want their position. We need to turn their position to relative positions, and we do that by using inverse transform point, and then it says it's simply a matter of comparing the Z of each foot. Okay, and whichever is higher, we have a boolean left, and we either mirror the jump or not. Okay, and that's just it. So that's how you mirror your animations based on your foot. And the last thing we need to see is how to play to find the incline between one animation or not. So we have obstacle forward, but if we keep it like this, the problem with that obstacle forward will have been that when you are going down a decline or an incline, I don't know how to call this, if you are looking for an obstacle forward, when you are over here and when you're doing a recast forward, well, then you do not have a way to know that this thing you hit over here, even if it doesn't hit right now, you have no way to know that you can actually walk over here. Okay, so that is a problem, as you can guess. Same with this, but we have kind of already seen this. Okay, so how we find this is after we have done the recast and updated the reference boolean we pass. So for instance, if we have updated the obstacle forward and that obstacle forward is it's true, then we're going to use a reflect on the vector 3. So what this does is reflect, say we have an incline, you do a recast over here, and that is basically going to reflect. The normal is this, then the reflection of the incoming vector will be this one, so we need this one. Okay, let's try this again because it turned a little bit pornographic. Okay, we have this, so we need to find this angle over here, and based on the angle do and check if there is actually an obstacle or not. So how we find that? Have our incoming vector, hit point minus the origin. The reflection vector will be, we need the reflection vector of hit point plus the origin. Origin in this case is the origin we pass over here. Okay, and the hit dot normal. The hit we assign it over here. There is no way the hit will be null, because if it's null, then the obstacle forward is not going to be true, because we pass the reference boolean over here. Okay, we have the reflect. We need to find the angle between these two, incoming vector, reflect vector, and if the angle is lower than 70, then that means it's not a steep angle, so that means we can actually walk, it's an incline and we can walk. So if obstacle is forward is true, I guess we could have just do this instead of using is hit. It would have been a little bit less confusing. Okay, we reset the obstacle forward to be false. If it's ground forward, and this is ground forward from the second this recast we do over here, okay, if it's true from this one, then we're going to check if horizontal or the vertical is not 0, so we're moving. So the other way we could have done this is if current state equals current state moving. Okay, then we need to find the angle. The other way we can find angles, you can choose either this way or this way, it doesn't matter, although I think this one will work a little bit better in this occasion. Okay, we have point 1, point 2. We need to find the difference on the y between those 2 points, and that difference is going to be assigned as a ground angle. We're going to start with a target incline. At this point, because we only have 2 animations, and you can actually use only 2 animations and fix everything else with the IK, using foot IK. And we're just going to hardcode values that we are declining or we are moving on an incline. Okay, but just keep in mind that if you implement a foot IK on top of this, it's going to be even better. So we're going to check if the ground angle is greater than a small threshold we have, so 0.3, then we're either going to assign it as 1 or -1 depending on the incline, and we go the opposite because the difference is also going to be the opposite. Okay, so if it's lower than 0, then the target incline will be 1, otherwise it will be -1. If the ground angle is 0, then it's going to stay 0, targeting incline be 0. And finally we assign that as the incline parameter of the animator, target incline, with 0.3 time dot delta time. And that's it. And there's that little part with the threshold we have over here is what controls that if you are actually on an incline like this and you are moving left or right, is that it plays the normal walk instead of the incline one or decline one. And when you are stopping, even if you are inside on an incline, you'll usually want to place the feet correctly with the feet with feet okay. So that's why I have this if statement over here. If you have other animations or if you have feet okay, you won't need this because it's not going to show, or you actually, yeah, you can correct the feet. It just goes back, it makes it go back into the idle state. Okay, so that's it. We've covered everything. We've covered everything that has to do with this controller. Now, this isn't the solution to all your problems. This is a great place to start, correcting all your problems. A few other stuff I want to say is, by looking and finding the angles for an obstacle, means that if I walk towards over here, it finds that this angle, and okay, it finds that this one, the angle to this one, is greater than the threshold we have. Okay, this angle, or basically the reflection of this angle is greater than the threshold we have, then it's an obstacle. But what you can actually cheat a little bit is, if you start walking like this, you can actually, so yeah, you have seen this in AAA games happening, but if you want to fix that also, I didn't bother with this in this video, is very simple. You can go into where you find the ground, when you do the raycast, okay, you have a raycast, you know what you're hitting, so you have, if you do transform.tag, just add the tag, add something. Okay, you know that you are on the ground, you can actually start doing checks depending, so what type of ground you are. So you can add a component instead of a tag. Never, I don't know why you want to compare stuff with a tag, but anyway. Okay, component, add something you want over here, say slide or obstacle, so when your player walks over here, start adding force the opposite of where he's moving, so he will go, so he will fall back to the ground. Okay, then you can play a different animation and all that. Okay, now we're done. I think I've covered everything I want to cover with this. Very simple. It's designed to walk really easy and change characters on the fly, and so easy, not on the fly. Okay, like this, and to work with a lot of characters. And it's also designed because we want to start working on other projects. Ignore that this character has not proper assigned accessories. Okay, because we want on some other projects I'm also reworking. Some of you already know that I'm reworking a major part, or almost everything inside the third-person shooter, but I thought this will also be useful as both as a project and as a tutorial series on their own. because, yeah, as I said, it can be used for a lot of different other games and different other types of games that I haven't covered yet or will cover in the future. So there's going to be another part later, probably this week or next week, or I don't know what week. Okay, that has to do with how we can take this and tailor it to work on the climb system. And you will have to wait for the third-person shooter, the new stuff we're going to see over there, and trust me, it's going to be just right. So, you know what to do. Like, subscribe. If you like what we're doing and want to keep it continuing and help me out with this, then consider supporting me on Patreon so we can continue. Or no, I know I say we, but I'm basically just me. I don't know why I'm saying, maybe it's me and my multiple personalities. Okay, so I can continue, keep making quality projects, quality videos like this. Okay, and because ad revenue doesn't exist if you're not PewDiePie, so yeah, it might exist for some other people. For me, it's like less than $100 that every 3 to 4 months. Okay, and all this stuff, I just takes so much amount of time to make, and it's nice so that we can continue keep making this for as long as we can, or as I can. Again, I don't know why I say we. So, you know what? The other way you can support me, if you do not like, or if Patreon is not your cup of tea, okay, is through Gumroad by picking a project or two, including this one. The 2 models I have over here, of course, they are not included. The Boxman is. So, okay, Patreon, Gumroad, like, subscribe, all that. Okay, I'm tired, and I'll see you fresh and new on the next video. Toodle-doo.